Hello, Prof. Moore here. I'm going to discuss acids and bases. What is acidity? Acidity is a tendency of a compound to lose a proton. A proton could be partially positively charged or fully positively charged, meaning it's electron deficient. If I look at HCl here in this reaction between ammonia and HCl, I know that the chlorine is more electronegative than hydrogen. Dipole moments will point towards chlorine, meaning chlorine will be having more electron density. Hydrogen will have less electron density. That's a proton right there. So these will play the role of a proton donor, and it's gonna play the role of an acid in that case. This is more acidic than ammonia because chlorine obviously is more electron withdrawing than nitrogen. Remember, electronegativity increases from left to right of the periodic table. Electronegativity is affinity for electrons. We discussed that in an earlier lesson. So this will mainly be the most acidic compound molecule because the hydrogen there is the most acidic based on electron withdrawal by the chlorine. The hydrogen is less electron rich out of the two, ammonia and HCl. So if this is playing the role of an acid, this will play the role of a base. But who on the molecule will accept the proton that is lost by the acid? Who on the ammonia molecule will accept the proton lost by the HCl? It will be the nitrogen because it has a lone pair. And again, nitrogen is more electronegative than hydrogen, we say. The dipole moments will point towards the nitrogen. So you expect that the nitrogen to be partially negative. And because of electron density there, and knowing that opposite charges attract, we'll use the two electrons to steal this hydrogen. That is arrow number 1. This process is called a mechanism. We are using a barbed arrow, double barbed arrow to show two electron movement. If it was half arrow, fish hook, that would be one electron movement. Okay, so we are making a bond between nitrogen and the hydrogen, and that bond is right there. Remember, any bond is 2 electrons. Okay, so once we steal that, these 2 electrons between the H and Cl have to go somewhere. They go to the more electron wanting, the more electronegative chlorine. So chlorine with 3 lone pairs now is going to have 4 lone pair of electrons, and it will have a formal charge of negative because the valency of chlorine is 7, but now you have 8 electrons, so you have an extra electron, you get negative. Otherwise, do the formal charge calculations. Formal charge equals to valency of the elements in the periodic table. Chlorine is in main group 7 minus non-bonding electrons, there are 8. There is no bond on it. It will be -1. That's another way to justify the negative. The nitrogen here, after gaining one more bond to the red hydrogen proton that it accepted, it will be positive. Nitrogen has a valency of 5, I believe, but right now you see it has a valency of 4. It's donating those 4 electrons for covalent bonding. Otherwise, you can do the formal charge calculation. Nitrogen is in main group 5, valency of 5 in the outermost shell, and then there are no lone pairs, and then there are 4 bonds. The answer is +1. Okay, so that's where the positive comes from. That's how you design, that's how you complete an acid-base reaction, and how you identify who was the acid, who was the base. Bearing a positive charge is a seller, telling us that ammonium ion here is going to be the conjugate acid. Okay, it came from the parent base, and then the chloride is going to be the conjugate base. It's a base right now, but it came from the parent acid. It's a base based on the negative charge. Let's define basicity. which I've already defined here, but I will give you another example. It's the tendency of a compound to accept a proton, which is what ammonia did. So here, who's gonna be the base? Who's gonna be the acid? I'll use the same idea, but this time I have an ionic compound. Now we have an ionic compound of sodium hydroxide. The sodium is gonna get a plus charge. Metals usually lose electrons to make a cation. The oxygen in turn will have a negative to balance it out. Okay, so I have OH minus, and like I said here, presence of negative charge tells me that's a base. This is gonna play the role of a base, and then I'm going to tell myself then this has to be the parent acid. And you can see that based on dipole moments from carbon to oxygen, oxygen is more electronegative than carbon, so it tends to have more electron pool. Okay, more electron pool, and of course the oxygen is pulling electrons towards itself. This hydrogen will be partially positive. So now I've identified my positive center, I've identified my negative center, and I've identified my acidic proton to take out. So I push electrons from the base to the partially positive hydrogen. So that is a bond being formed, which will be in between here. Okay, so HO to the red hydrogen, that's the new bond being formed, which is what you're forming here by arrow 1. And then we don't stop there, we have to push another bond from another arrow from the bond to the oxygen, because oxygen is more electronegative, so it will want to take those electrons between OH. You have 2 lone pairs, now you're gonna end up having 3 lone pairs. Formal charge calculations must be done. Oxygen is main group 6. I have 6 non-bonding electrons. I have 1 bond. The charge will be -1, hence the negative. Again, this is a base, but it's on the right. I'm gonna call it a conjugate base. Part was the acid, and then the water formed here will be the conjugate acid, which was formed when the base took out a hydrogen. Moving on, water can play the role of a base and an acid, but in this case it's going to play the role of an acid. Like I said, in the case of HCl, the H is more acidic because of dipole moments. The chlorine will take partial negative charge, so we expect the water to take out that hydrogen using its oxygen, using the lone pair oxygen. And as it takes out that acidic hydrogen, knowing that oxygen here is partially negative because of dipole moments, remember again, oxygen is more electronegative than your hydrogen. By the way, hydrogen will be somewhere here. So oxygen is partially negative in water. It uses its lone pair. There's more electron density here to take out the hydrogen, arrow 1. And then, like we said, this bond will break. This bond will break towards the more electronegative chlorine. And in that case, you're going to get, from H2O, you'll get H3O plus. We call that hydronium. That's a hydronium. Get used to this vocabulary. You have a new bond from arrow 1. That new bond right there. Those are the 2 electrons that are now being used to make a bond, and the valency and the formal charge of oxygen will change from neutral to positive, because now you have 3 bonds. If you want to confirm, the formal charge of the oxygen will be equal to, oxygen has a valency of 6, there is 2 non-bonding electrons, and then there's 3 bonds. So 3 bonds around the oxygen, you'll get +1. So the oxygen on water has +1 because if you do the calculations of formal charge, you get +1. Okay, and then the chlorine left, it originally had 6 non-bonding electrons. Now it has 8 of them. Like we did the calculations here, formal charge of the chlorine, you get -1. So this has a positive charge, that will be the conjugate acid, and the chloride is going to be the conjugate base. So that's the general idea on acidity and basicity.